Have you ever wondered how ChatGPT can suddenly access GitHub, your local files, Slack databases, or even control applications? Is it using APIs or is it using plugins or is there something completely new? The answer is Model Context Protocol or MCP. And in this video, I'm going to explain MCP in three levels of difficulty. If you are a beginner, you will understand it. If you are an AI engineer, you will appreciate it. And if you are an architect, you will know exactly why everyone is talking about MCP. Let's start with the easiest explanation. Imagine you have a very smart friend. You ask him, "What's the weather today?" He replies immediately. Now imagine you ask, "Can you book me a flight?" Suddenly, your smart friend has a problem. He doesn't actually know how to open airline websites. He doesn't know how to log into your Gmail. He doesn't know how to access your calendar. He is smart, but he is trapped inside a box. That's exactly how an LLM works. It knows language, it reasons extremely well, but it cannot directly interact with external systems. This is where MCP comes in. Think of MCP like a universal adapter. Just like USB-C lets your laptop connect to many different devices, MCP lets an AI model connect to many different tools using one common language. Instead of building a separate integration for every AI model and every application, everyone simply speaks MCP. Now let's understand the real problem that existed before MCP. Imagine you have three AI applications, maybe a chat assistant, an IDE copilot, and an AI agent framework. Each one is intelligent, but each one has a limitation. They only know what's inside their own context window. If they need information from outside, they must call external tools. Now think about the number of tools inside an enterprise. A PostgreSQL database, internal APIs, CRM systems, ticketing platforms, email services, file systems, weather APIs, and many more. Without a common standard, every AI application needs a separate custom adapter for every tool. Look at the center of this diagram. It's a complete web of connections. Every red line represents another integration to build, another integration to test, another integration to secure, and another integration to maintain. As more AI applications are added, the number of integrations grows rapidly. In this example, three AI applications multiply by five tools, which gives you 15 separate integrations. Now imagine an enterprise with 20 AI applications and hundreds of enterprise systems. You are suddenly managing thousands of custom integrations, different APIs, different authentication methods, different SDKs, different maintenance cycles. That's why teams spend more time integrating than actually building AI features. This is exactly the problem MCP was designed to solve. Instead of every AI application talking to every tool differently, everyone speaks one common protocol, one language, one standard, and dramatically fewer integrations to build. Have you ever wondered what actually happens after you ask ChatGPT a question that needs data from your database, Gmail, or your local files? Does the AI directly connect to all these systems? Not really. There is an entire architecture working behind the scenes. Today, let's understand how a request flows inside an MCP architecture, step by step. Let's start from the top. Everything begins with host. The host is simply the AI application you are using. It could be Cloud Desktop, Cursor, VS Code, or any AI powered application. Suppose you ask, "What are this month's top sales?" Your request first reaches the host. The AI model understands your question and immediately realizes, "I don't have this information inside my knowledge." So instead of guessing, it decides, "I need to use a tool." That's exactly what's happening in step 2. Now the request enters the MCP client. Think of MCP client as a communication manager. It has three important responsibilities. First, the router. The router figures out which server can answer this request. Should it go to the database? Should it go to email? Or should it access the file system? Once the destination is identified, the request moves to The next component, message translation. Every AI model speaks its own internal language. Servers, however, expect requests in the MCP protocol. So the message translation layer converts the model's request into a standard MCP message that every MCP server understands. Finally comes the response handler. Its job is to receive the response later, validate it, format it properly, and prepare it for the AI model. At this point, the client sends the request to the appropriate MCP server. Now we are inside the execution layer. Here, different MCP servers expose different capabilities. For example, a database server retrieves sales data, an email server can search or send emails, a file system server can read documents or local files. Besides these servers, MCP can also expose tools, resources, prompts, depending on what the AI needs. The selected server performs the requested action and returns the result back to the MCP client. Now the response handler receives the data, it converts the MCP response back into the format that the AI model understands. The AI combines this external information with its reasoning ability, and finally, you receive an accurate answer. All of this happens within just a few seconds. So that's the complete MCP request flow. Host receives the request, MCP client routes and translates it, MCP server executes the action, the response comes back to the model. This standardized architecture is exactly what allows AI assistants to secure interact with databases, enterprise applications, APIs, emails, file systems, and countless other tools without needing custom integrations for every application. We've already learned how an MCP request flows from the host to the MCP client and finally to the MCP server. But here is the next question. How does the host actually communicate with the server? How is security maintained? And where do these MCP servers actually run? Let's understand the complete MCP ecosystem in just a few minutes. Let's begin with the transport layer. Think of it as the communication channel between your AI application and the MCP server. There are two common transport mechanisms. First is STDIO. STDIO stands for Standard Input and Standard Output. This is used when the MCP server is running on your own machine. For example, suppose you are using Cursor or Cloud desktop. You have an MCP server that can access your local files. The host simply launches the MCP server as a local process and exchanges messages using JSON RPC through standard input and output. No internet required. It's extremely fast and ideal for local development. The second option is SSE or server sent events. This is used when your MCP server is hosted remotely. Instead of launching a local process, your host communicates over HTTP. This is perfect for cloud applications where the AI needs to access enterprise systems, remote databases, APIs, or SaaS platforms. So remember this simple rule: STDIO for local, SSC for remote. Now comes the most important part: security. Giving an AI access to your system is powerful, but it also needs strong protection. The first layer is authentication. Every MCP client and MCP server verifies each other's identity. This could be through your API keys, OAuth, or access tokens. Only trusted clients are allowed to connect. The second layer is user consent. Imagine the AI wants to read your Gmail or access your Google Drive. It cannot simply do it automatically. You will first receive a permission request. Only after your approval does the MCP server execute that action. So you remain in complete control. Next are audit logs. Every request, every tool call, every action gets recorded. This is extremely useful for compliance, debugging, and security investigations. Finally, there is supply chain risk. Not every MCP server available on the internet should be Trusted. A malicious server could expose sensitive information. That's why organizations validate, sandbox, and monitor every MCP server before using it. Which brings us to an important principle shown at the bottom. Trusted tool boundary. Only trusted MCP tools should ever be allowed to access your data. Now let's see where MCP servers actually run. The simplest option is local deployment. Everything runs on your own laptop or workstation. This gives you maximum privacy. No external network, perfect for local files, coding assistants, and sensitive information. For enterprise applications, we usually use cloud deployment. There are two popular options. The first is containers using Docker or Kubernetes. Organizations can deploy MCP servers that are scalable, portable, and always available. The second option is serverless computing. Platforms like AWS, Lambda, Azure functions start only when required. This reduces infrastructure costs because you only pay when the MCP server is actually being used. Finally, notice the comparison at the bottom. Local servers provide the maximum control and privacy. Remote servers provide better scalability and enterprise integration. The choice depends entirely on your use case. Now, if you combine everything we have learned, here is what happens. A user sends a request through the AI application. The host communicates using the appropriate transport layer. The request reaches the MCP server. The security layer verifies permissions, authentication, and trust, and then the server performs the action. And finally, the response flows back to the AI model. That's the complete ecosystem. So here is the simplest way to remember MCP. Level 1. MCP is like a USB-C connector for AI. It standardizes communication between AI models and external tools. It enables secure, scalable, enterprise-grade AI applications without building hundreds of custom integrations. If you are learning AI agents, MCP is one of the most important technologies to understand in 2026. And trust me, you are going to see it everywhere. If you found this video useful, don't forget to like, subscribe, and share it with your friends. I regularly create practical content on AI, generative AI, MCP, Agentic AI, RAG, and enterprise architecture. Thanks for watching, and I'll see you in the next one.